right, in Unit 13.2, we are looking at ways to arrange numbers or letters or objects in groups, and those are called permutations and combinations. They're very similar, but the distinction between them is we need to know, does order matter? Okay, does the order of the items that we choose, does it matter which order we choose them in? In a permutation, it is an ordered arrangement. So yes, order matters here. Okay, order matters. And we're arranging objects in different orders. So we have three types of permutations that we're going to look at. We have distinct objects with repetition. Now the word distinct means that you can tell them apart. Okay, an R and an N are different. You can tell those apart. A 1 and a 7 are different. Can you have repetition? That means, can you use a same letter or number more than one time? So we could have objects with repetition, we could have distinct objects without repetition, and we can have not distinct objects where you can't tell them apart. And I'll point that out when we get to that. But in this first example, it says that the International Airline Transportation Association assigns 3-digit codes to represent airport locations. For example, Detroit Metro Airport is DTW, and that's known all over the world. For Detroit Metro Airport, they use the same 3 letters, DTW. Fort Lauderdale is FLL. I know Orlando is MCO. Okay, so each airport has their own 3-letter code. If repetition is allowed, we can repeat the letters. That means we can have an AAA if we want. How many airport codes are possible? So we have 3 spaces that we're going to put letters in, and these are all letters. And they can repeat. So I can choose any of the 26 letters in the alphabet to go first, and then I could use any of the 26 letters in the alphabet to go second or to go third. So this is the same thing as 26 to the 3rd power, which is, at my calculator, I did this, it's 17,576. So there's 17,576 ways to come up with 3-letter codes for airports. Okay, so if I have repetition, I have the number of objects that I have to the number of places that I'm going to put them. In this case, I have 26 letters in the alphabet, and I'm going to choose them 3 times. I'm going to make 3 choices. In example 2, suppose that we wish to establish a 3-letter code using any of the 26 uppercase letters of the alphabet, but we require that no letter used more than once. How many different 3-letter codes are there? So here there's no repetition. R-E-P-E-T-I-T-I-O-N. There we go. No repetition, but we still have 3 letters, and in the first spot, I can choose any of the 26 letters, but once that letter is chosen, I can't use it again, so that there are only 25 letters to choose from. And then I take one out, and there would be only 24 letters to choose for the third spot. And if I multiply these together, 26, 25, 24, that is 15,600 ways that I can get a 3-letter combination, okay, where I cannot repeat the letters. So this is called a permutation, and we have a math symbol for that, math notation, and that's P, where we have a permutation of our number of items choosing R at a time. All right, so up here we had the permutation of 26 letters, and I'm going to choose 3 of them. And repetition is not allowed for this. Okay, so 26 items, choosing them 3 different ways. In example 3, it says, how many ways can 5 people be lined up? Now, let's think about where they're going to stand on the sidewalk. I have 5 spaces. So if I take Sally and say, okay, Sally, you are the one of the 5 people that are going to stand here first. But I take Sally, say, you're going to stand here. There's only 4 people to choose from for the next spot. And then there's only 3 people to choose from the next spot, and then 2, and then 1. Now, when I'm multiplying these together, in math, we like to use shortcuts whenever we can. And this actually is called 5 factorial. It's not showing excitement. It's just starting with this number and multiplying every number below it until you get to 1. So if I have 6 factorial, I would have 6 times 5 times 4 times 3 times 2 times 1. 5 factorial starts at 5, multiplies every number until we get to 1. Now I can either put all of those numbers in on my calculator, or I can actually do this on Desmos, where I start with 5. So I'm going to go back here. There's my home screen. I'm going to start with 5, and then to find the exclamation button, it's actually down here. And if I put that there, it calculates for me 120. So 5 times 4 times 3 times 2 times 1 is 120. So there's 120 different, orders of people to line up. All right, so if I want to then look at permutation of objects that are distinct without repetition, so I cannot repeat any numbers, letters, or elements. I have the number of permutation. I start off with a total number of items, and I'm choosing them R at a time. All right, so there's a formula for that. We'll take n factorial and divide it by n minus r factorial. These are nope, I'm not going to say that here. Never mind. Okay, so n factorial divided by n minus r factorial. All right, so just a note here, if you ever see 0 factorial, it's just, how do I want to say that? It's something that we're just going to trust that the value of that is 1. All right, 0 factorial is 1. It's not 0. And then I have 1 factorial is just 1. So 2 factorial is 2 times 1. But this is the one that kind of gets people. It's just a definition. 0 factorial is 1. Now in example 4, if I'm evaluating this permutation, I have 7 items and I'm choosing 3 at a time. So that's my R. Now using the formula, I'm going to have n factorial, so I have 7 factorial over 7 minus 3 factorial. Oops. There. So this would be 7 factorial over 4 factorial. And if I were to write this out, do this here, I have 7, 6, 5, 4, 3, 2, 1 over 4 times 3 times 2 times 1. So these are all going to cancel. And I'm really left with 7 times 6 times 5. And that would be 30 times 7 is 210. Okay. In part B, I'm going to do that one on top because that gives us a little room here. I'm going to have 6 factorial over 6 minus 1 factorial, which is 6 factorial over 5 factorial. Now that remember, this is 6, 5, 4, 3, 2, 1 over 5 factorial. And see how these cancel. Whoops. But I'm just left with 6. All right, here's another one. Bigger numbers here. 52, choose 5. All right, so I have 52 is my n over 52 minus 5 factorial. Now this is 52 factorial over 47 factorial. Now I can do this on Desmos. Let's get that back here. So I can type in 52, get to the factorial, and then back to the front side. Oops. I want to divide it by 47 factorial. And this gives me, I don't think I have that right number. 52 divided by 47. Oh, I don't have that number because I didn't calculate it. Would be 311875200. So basically what I would have here is 52 times 51 times 50 times 49 times 48. 1, 2, 3, 4, 5. Okay, now 47 factorial is going to cancel with the 47 factorial up here. So these are the numbers that are left to multiply, and that again was 311875200. 311,875,200. So now let's say that we have permutations that have objects that are not distinct. Okay, so what that means is they're not all different. So the number of permutations in which some are one kind and some are another kind, we are looking at this formula here where we talk about n factorial and then we divide it by all these things that are repeating. Or I call them the repeaters. Okay, so here's a great way to look at this. We have the word rearrange. Now, if I were to count the numbers here, the number of items in this word is, I believe, 9. But if you notice, I have R 3 times. So my R is repeating, there's 3 of them. I also have an A there twice. And something else, I have 2 E's as well. So in my formula, it says to take the number of items, 9 factorial, and then I'm going to divide by the repeaters. So my R's are there 3 times, so that would be 3 factorial. A's are there twice, 2 factorial, and E's are there twice. So these are the repeating letters, the number of repeating letters. So if I were to calculate this, I'm going to go back here. I have 9 factorial, and I'm going to divide that by, and now on the bottom, I'm going to put in parentheses because I want all of this on the bottom, 3 factorial times 2 factorial times another 2 factorial. And if we look at what we have here, we have 15,120. So this is 15,120. Zoom back out here. So those are distinct ways to rearrange the letters in the word rearrange. Okay, not counting if this R and this R are swapped. That's the same appearance. So that's why we're dividing by all these things that are repeating. All right, so let's try the word Mississippi. All right, so if I count the letters, I have 11 letters. I have some that are repeating. I have I's, and there are 4 of them. I have S's, and there's 4 of those. And I have P's, which are 2. So according to this formula, I'm going to do 11 factorial divided by 4 factorial, 4 factorial, 2 factorial. Okay, so on Desmos, I can put in 11 factorial, and then I'm going to divide it by 2 factorial, and then 4 factorial and 4 factorial. And I didn't put parentheses here, but as long as I see that all of these numbers are on the denominator, I'm good. And over here, it shows I have 34,650 arrangements of these letters that all look different. All right, so here, the order in which we put them matters, okay? In the next page, and this is going to be a part 2, but I think it's short, so we're just going to do it all together here. Now we're looking at combinations. We're making groups of things, but the order doesn't matter. Okay, so a combination is just a group of things. It could be a group of letters, numbers, people, but the way we have them doesn't matter. So we have all of the objects are different. Once it's used, it can't be repeated, and the order is not important. So we have this other formula for a combination. same, the variables are the same. N means how many total items do we have and how many are we going to use. So it says to list, okay, it doesn't say how many here. At first it says to list all the combinations of 4 objects, A, B, C, and D, taken 2 at a time. So I want 2 of those letters in a group. So first of all, I'm going to say that AB is the same thing as BA. Doesn't matter which one comes first. This is the difference between a permutation and a combination. If it doesn't matter, then these are the same. If these are not the same, then we're talking permutations. So if I make a list, I'm going to have A and B together, A and C, and A and D. And I could have B and C, B and D, and then I can have C and D. So there's 6 different ways to group those letters together in groups of 2. So that's a combination, 4 letters, putting 2 at a time. Now if I were to use this formula, I have 4 factorial over 4 minus 2 factorial, so that's 2 factorial, and then r is another 2 factorial. So I'm going to just multiply this one out. 4, 3, 2, 1 over 2, 1, 2, 1. Okay, so I can cancel common factors. So what I'm going to do is I'm going to say, okay, 2 times 2 is 4. And then I have left 3 times 2 times 1, which is 6. And that's the number of items that I made in my list over here. So here we can use our formula to find the value of 3 objects, choosing 1 at a time. So in my formula, I would have 3 factorial over 3 minus 1 factorial, which is 2 factorial, times 1 factorial. So this is 3 times 2 times 1 over 2 times 1 times 1. So basically, I have 3. I have 3 things, and I'm going to choose a group of 1. And there's 3 different ways to choose that. All right, so I could use my my formula, and I didn't do this with permutations, but if I go back to my Desmos, in the menu where it says functions, if you look under statistics, you will see that down here we have combinations and permutations. So this would be a combination of a number of things, choosing r at a time. So example, I have 6 things, choose 2 at a time. I can do this with combinations, and I can do this with permutations. So for part B, I have a combination of 6 items, choose 3 groups of 3. So I can do this as combination. Oops, here we go. I have 6 items, and I'm going to put a comma there, and I'm going to choose groups of 3, and it tells me that I would have 20 different combinations. Okay, so that's another way to check your work. That's the same thing as 6 factorial. 6 minus 3 is 3 factorial, and then 3 factorial again. That would give me 20. If I have, oops, I'm sorry, I forgot to zoom back out. Combination of n items, choosing 0 at a time. All right, so I have a group of things, and I'm not going to choose any of them. How many ways can I do that? Now, mathematically, let's look at this. This means I have n factorial And then on the bottom, I have n minus 0 factorial, and then 0 factorial. Now, we said before that 0 factorial was 1. So this is the same thing as n factorial over n factorial. And that would be 1. In part D, I have 52 items and I'm choosing 5 at a time. Now this is a common occurrence that we're going to see, especially when we get to probability, because this describes a poker hand. I'm choosing 52 items and I need a group of 5. It doesn't matter if I get the 3 of clubs first or if I get it fourth. I still have it in my hand. So that would be a combination. So the formula is 52 over 52 minus 5 is 47. And then I'm going to divide by 5 factorial. And if I do this here, 52 factorial divided by 47 factorial, and then 5 factorial. Holy moly, oops, that's because I didn't get all of this up here. This is 52. 52 factorial. There we go. That looks much better. Here I have 2,598,960. 2598. What was my number again? 960. Okay, so this is the number of different poker hands that you can have. All right, so if you think about that, only 4 of them are a royal flush. There's only 4 ways to do that out of this. And we'll talk about that later when we get to probability. So in the last example here, it says, how many ways can a committee be formed from a pool of 7 students? Well, one thing it doesn't tell us is we need to know how many people are on our committee. And I think that was just left out. Let's say there's 3 people on a committee. So that means it doesn't matter who comes first or second or third. I have 7 people and I'm going to choose 3 at a time. And the order that I choose them doesn't matter. That's why it's a combination. So this would be 7 factorial. Then I subtract them. I get 4 factorial and then 3 factorial. And if I calculate this, I am going to have, I can actually do this by hand. I have 4, 3, 2, 1 factorial. The 4 factorials cancel. And then I have a 3 times 2 times 1 left with a 3 factorial. And that goes into 6. And there's 35 ways that I can choose groups of 3 from a group of 7 students. All right, so you're going to have lots of practice on this. Make sure the difference between, the difference between combinations and permutations, and that is, does it matter which order they're chosen in? Okay, if it does matter, it's a permutation. If it does not matter, it's a combination.